All right. There's my pebble. Okay, and then here's the ripples coming out of the pond. And it says, at what rate is the total area of the water changing? So we're finding dA dt, the rate of the area over time. We are told we're looking at the time that the radius is 4 feet. And we are told that the radius is increasing at a constant rate of 1 foot per second. So that's dr dt, the rate of change for the radius. And let's see, the ripple is coming out in the form of circles. So if only we had an equation that related the area of a circle to its radius. Let's try pi r squared. So then dA dt is 2 pi r times dr dt. And then we plug in 4 for r and 1 for dr dt. And our units are in feet squared per second. How many got it right? Good, 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 good. Any questions on that one before we go on? Time to make them harder. Oh, we did that one. That's the one we ended with last time. Okay. All right. Baseball diamond has the shape of a square with sides of 90 feet long. All right, here we go. Okay. I don't like the way second base is like all the way up here. Let me try that again. Bit better. I'll take that. Exactly like it. All right. A player is running from second base to third base. In case you don't know, that is here in the spaces between second base and third base is here. So there's somewhere here. And we're looking at the rate of change of their distance from home plate. So the player's distance from home and we're asked to call that distance S, so I'm going to call that distance S. And we're asked what rate is that player's distance from S from home plate changing. So we are trying to find ds dt. We're trying to find ds dt. All right, and I'm going to show this next thing a little bit differently than I did yesterday. If you wanted to think about it the way that we talked about yesterday, I'll explain that too. But I'm going to show it a little bit differently this time. This distance is 90 feet. and that 90 feet stays 90 feet. No matter where the player is, this distance stays the same. The distances that change, let's see. Oh, is the distance from third base. So this distance is changing. So another way of saying this is, yesterday we said it as, that means that the distance between third base and home plate, maybe we called y, and said that dy dt was 0. So the rate of change of that distance was 0. Another way of saying it is that because it's a constant, because it's not changing at any particular rate, we don't need to write down a rate, because it's going to be a constant, and so when we take the derivative of that constant, it's going to be 0. So we can treat it as a constant. Now, x, we are putting as a variable because it is changing. The distance of 90 feet is not changing, so I'm writing it as 90 feet. And this is going to be another Pythagorean theorem question. I'm not just drawing it as third base. I'm drawing that as a right angle to make a right triangle. So let's see. In this case, x is 30. And dx dt is what? No. You need to put something on that number. Well, yes. Something else. This distance is getting smaller, right? Because they're running towards third base. So this distance is getting smaller, so the rate of change of the distance is negative. So our dx dt is negative 28 feet per second. And you should be able to make a prediction as to whether this rate is going to be positive or negative. If they're moving closer to third base, is this distance from home going to get bigger or smaller? So that means that that rate of change should be negative as our answer. That's a big part of why putting this negative sign here is going to make a difference. All right, our hypotenuse is S. So in Pythagorean theorem, that goes by itself on this side, equals x squared plus 90 squared. So much in geometry mode that I just wrote a degree symbol on the 90. All right, 90 squared. Again, I just want to explain this one more time. The difference between me saying this is 90 feet in the diagram and putting an x here and saying that x is 30 is that this 90 feet stays constant. And so we don't have to treat it as a variable. We can just treat it as a constant at 90 feet. This distance x is changing. It has a dx dt, and so we are treating it as a variable because it's changing. It varies. And we are defining it at that point to be 30. That's the idea. So let's take our derivative here. Derivative of s squared is 2s ds dt, since we took a derivative of s. Derivative of x squared is 2x dx dt. Derivative of 90 squared is 0. And we get the same result as we would have if we eventually had put in that this rate of change was 0. It would still cancel out and be 0. All right. We're trying to solve for ds dt. So we should be able to figure out what all these are. Well, x is 30. Dx dt is negative 28. What is s? It's Pythagorean theorem time. Here we go. Sorry. Hypotenuse, s squared equals 30 squared plus 90 squared. Yes. S squared is 9,000. This is 8,100. This is 900. So 8,100 and 900 is 9,000. So now we have all the pieces plugged in. Notice that we had to use Pythagorean theorem to get what s was. ds dt, when I solve, will round to negative. Hey, it was negative. How about that? 8.854. And that is in feet per second. We'd be dividing by 2 square root of 9,000. Okay, questions on that? All right, let's do one more here. A water tank in the shape of a right circular cone has a height of 10 feet. The top rim of the tank is a circle with a radius of 4. If water is being pumped into the tank at a rate of 2 cubic feet per minute, what is the rate of change of the water depth in feet per minute when the depth is 5 feet? There's my cone. Top rim of the tank is a circle. With a radius of 4. And this height right here, which will also be depth when we were talking about the water. This distance is 10. Now, we can use those ideas but we'll use the 4 and the 10 in some way. But for right now, that is not there is not the entire tank getting filled yet. So we're going to put some water. Okay, there's my water. And then I will give you a minute to write down some other quantities that we know. We are trying to find what? The rate of change of the depth, which I'm going to write as height. That's the same as the height of the cone at that time. So I'm going to write it as dH dt. What is the 5? Okay, so what equals 5? The depth, so, which we are labeling as h. You'll see why in a second. Two is what? Okay, so we're going to label that as dV dt. So first clue is that it's the rate of the amount of water being pumped into the tank, which is what volume measures. Clue number 2 is that it's in cubic feet per minute. So that sounds like a volume. That sounds like a unit for a dV dt. Volume of a cone, as you all know, is 1/3 pi r squared h. Now, we are given h, we are given dH dt, and so what I'm going to do is to write the radius in terms of the height and put that in for r, so that I only have one variable. Because if I had two variables, if I tried to do dV dt from here, this would become a product rule, and the problem would get more complicated. It would still be solvable, but it would be harder. So I'm going to cut out that step right here and write everything in terms of h. So what is r in terms of h? What is the size of the radius in terms of the height? Well, when the height was 10, the radius was 4. The depth right now is 5. What's the radius going to be? It's going to be 2. The radius is half of, the depth is half of it, and so the radius will also be in half of it. It's proportional. So it is, the radius is 2/5 of the height. Whatever the height is, take 2/5 of it, and we get the radius. So instead of using r and writing out a big product rule, I'm going to take that 2/5 h and put it in for r. Oh, let's see. 2/5 of I squared is 4/25 times 3 is 4/75 times pi, and then h cubed. And now it's time to take our derivative. Now we have it in terms of one variable, which is going to be much easier on us. dv dt equals 4/75. 4/75 pi is a constant out in front. Times derivative of h cubed is going to be 3h squared dh dt. So this 3 will cancel with this 75 to be 4/25 pi times h squared dh dt. So we're going to be plugging in to solve. Remember, we're solving for dh dt. So dh dt is going to be the only thing we're not plugging in. We know dv dt. dv dt is 2. We know h is 5. And then we can solve from there. I'll show one more step here. 5 squared is 25, so this will cancel with the 25 here on the bottom. So dh dt, if I divide, should be 1/2 pi. And since it's a rate of change of the height, now my units are going to be feet per minute as our units. So again, just to recap, since we didn't care about r and we didn't care about dr dt, and we were just solving for dh dt, I wrote everything in terms of h so that I wouldn't have to deal with a product rule and r and dr dt throughout the rest of the problem. That was kind of the new step added into this.